Okay, every lab scientist out there knows this feeling, right? You have an assay that works perfectly on a good day, but the big question is, will it work reliably every single day? We're talking about the difference between a fluke and a truly robust method. This is all about building reliability in from the start, not just checking some box at the end. So let's dive into how we do that. This is really the million-dollar question, isn't it? It's not about whether your assay can work under these perfect, ideal conditions. It's about whether it will work when the real world, with all its messiness and tiny variations, inevitably shows up at your bench. And this is exactly what real life in a lab looks like. We're not talking about some massive, catastrophic failure. No, it's the 100 little, totally normal things. A different person running the plate, the room is a couple of degrees warmer today, or you get distracted for just a minute during a wash step because, the phone rang. Any one of these can absolutely sink a fragile assay. So what's the deal? Why are these seemingly perfect methods so fragile? The big problem is that way too many teams discover these hidden weaknesses way too late in the game, like during validation or tech transfer, and by then, trust me, it is incredibly painful and super expensive to go all the way back and fix it. The solution is to get ahead of it by thinking about robustness. And what's so important about this definition is that phrase, small, deliberate changes. This isn't about just creating chaos. It's a planned, structured process where you intentionally nudge the protocol in ways that mimic that real-life drift just to see if it can handle the pressure.
And this is why immunoassays are especially tricky customers. They're not simple A plus B equals C systems. They're these complex webs where everything is connected. The coding density interacts with your blocker chemistry. Incubation time interacts with temperature. This coupling means a teeny tiny shift in one thing can cause these unexpected ripple effects, making an assay that looked perfectly optimized suddenly fall apart.
And let me tell you, not dealing with this early on has real, tangible costs. So let's look at the 3 most common and definitely most expensive ways a fragile assay can come back to bite you. Okay, first up, hidden sensitivities. This is where something you thought was totally minor, like a 5-minute delay, turns out to be absolutely critical. Then there's lot-to-lot fragility. And come on, we've all been there. A new batch of antibodies shows up and boom, your assay window just collapses. And finally, the dreaded transfer shock. The method works like a dream for you, but the second it goes to a new site or a new operator, it completely fails. So here's the bottom line. Don't get bogged down arguing about what to call it. Robustness, ruggedness, whatever. The name doesn't matter. What really matters is that you're proactively testing for this realistic drift so you find the problems before they find you. All right, let's turn the corner and talk about the solution. Instead of just relying on random, one-off checks here and there, we can use a much smarter, more structured approach called design of experiments, or DOE, to intelligently stress test our assay. Think about it. The old way of testing one thing at a time, it's slow, it's piecemeal, and worst of all, it completely misses how these different factors combine and interact in the real world. The DOE approach is totally different. It's an efficient, structured stress test that looks at multiple factors all at once. It doesn't just ask what if, it directly answers the most important question of all. Which of these variations actually matter? And please, don't let the name design of experiments scare you off. The goal here isn't to generate some 50-page statistical report that no one can understand. The goal is a simple, powerful set of decisions. It's a clear list that tells you exactly which parts of your protocol you have to lock down, and which ones have a little more wiggle room. So, how do you actually do this? Well, it's not as complicated as it might sound. Let's walk through a pretty straightforward 7-step blueprint that you can apply in your own lab. So first, you've got to define what success even looks like. Then, you list all the things that might vary. You choose realistic ranges for that variation, and you pick a simple experimental design. After you run the experiment, you analyze the results to make clear decisions. And finally, you turn those decisions into a rock-solid control strategy. Now, I really want you to focus in on step 3, because it is arguably the most important one. You have to choose ranges that reflect that realistic drift we've been talking about. We're not trying to push the assay until it breaks, no. We're testing a plausible temperature shift of, say, plus or minus 3 degrees, or an incubation delay of 15 minutes, things that could actually happen on a busy Tuesday afternoon. And when it's time for analysis, keep it simple. Seriously, you're looking for a ranked list of effects. Which factors move the needle the most, and in which direction, up or down? The ultimate goal here is to create a top drivers list that tells you exactly where to focus all of your attention. Okay, so all of this work leads to the big payoff, a clear data-driven control strategy. This is the thing that transforms all that experimental effort into everyday, reliable results. And this table is a perfect illustration of what that looks like in practice. Your DOE might tell you that wash-soak time is a high-risk parameter. The result? Your SOP gets a strict guardrail, 0-second soak time, period. But it might also show that adding an extra wash cycle is actually low risk, which gives your operators some flexibility. It's all about being strict where you have to be and flexible where you can be. So at the end of this whole process, what you have is a complete robustness package. This isn't just a protocol anymore. It's the protocol plus a guide to its sensitivities. It includes those clear guardrails, specific training notes for new team members, and crucial transfer notes that are going to prevent that transfer shock when the assay moves to a new lab. So if there's one thing you take away from this, it's this. Do this work early. Don't wait for robustness to be some last-minute checklist item you do before validation. By testing for it right after you get a baseline method working, you are building reliability in from the ground up. This will save you countless hours of troubleshooting later and makes your final validation so much more predictable. And that really leaves us with one final thought. I want you to take a hard look at your own methods and ask yourself this question. Is this assay truly built for the real world, or is it just designed for a perfect day on the bench? The answer to that question can make all the difference.